We'll get started in just a moment. Everyone, do you have any questions right now before I start? No, we're okay. I'm trying to remember how far we got here. We got to C on these notes here. How about D? Did we look at D?
I don't think so.
I don't think we looked at D. Okay, let's do D. Move this over here. Okay, so we're going to be doing integral 2x squared minus 4. I'm sorry, minus x plus 4 over x cubed plus 4x dx. All right, so last class we established kind of the standard way that we go about these partial fraction problems. You know, what we do when we see a linear factor in the bottom, what we do when we see a repeated linear factor. We started to talk about what happens when you have a quadratic, irreducible quadratic factor in the bottom, and that's where this problem is going to lead us. So first thing we always want to start with here is long division if we need it. So do we need long division here?
No.
No, right? Because the power on top is smaller than the power on the bottom, so no long division. So what I'm going to do next is try and factor just the denominator. So I try and factor. I can pull an x out, right? And that's about all I can do. We cannot split up the x squared plus 4. If it was a minus 4, we could split it into a difference of squares, but we can't. And so that's where we are. So let's talk about these things that we have here. This right here is a linear factor. And then this right here is a quadratic factor. And it's irreducible, meaning we cannot break it down, right? We can't factor that. So we're going to start our partial fractions on the side here. I'm going to rewrite the entire thing. All right, and now let's start putting together what we need for the partial fractions. So how am I going to handle the linear factor x? What am I going to put over here?
A over X.
A over X. So just a number over the linear factor. Plus, now, how do we handle irreducible quadratics? We're gonna put it on the bottom, right? But what do we put on top?
Bx plus c.
X plus c. All right, now, last time we talked about the short method and the long method, right? So let's see what happens here. I'm going to clear the fractions first. So that means I'm going to multiply both sides by this denominator. So I do it over here. That'll clear this out, and then I have to do it over here. So this part is just algebra, right? But, you know, maybe it's been a while since you've done it. We're just clearing things out. So when I multiply here to here, the x's cancel, the a stays, the x squared plus 4 stays. And then when I multiply here to here, the bx plus c stays. The x squared plus 4 cancels, but we still have an x there. So at this point, maybe, I don't know if this is obvious or not to you, but the short way is not going to work very easily because, like, let's say I'm going to try and get A. Then I've got to, well, I mean, I guess we could get A. How could we get A easily?
By setting x equal to 0.
Yeah, if we just set x to 0, if that was 0 right there, then it would kill off everything over there. Yeah, so we could get A. All right, but what about if we try and get B or C? What's the problem with that? We try and get B or C. Can you kill this off? Can you ever kill off x squared plus 4?
Yeah,
No, right? There's no number you're ever going to be able to plug in for x that when you square it and add 4, you get 0, unless you're using imaginary numbers, which we're not allowed to do. So there's no way that we're ever going to be able to kill that piece off. So I'm going to go to the long way, all right? So the long way means just multiply everything out on the right side. Okay, so I distribute the a through here, ax squared. If you have any questions, just stop me, all right? I'm going to be moving a little quick today. bx squared plus cx. All right, I'm going to collect my x squareds together. So I have an ax squared and a bx squared. So what I'm going to do is put those together. I'm going to factor the x squared out. Then I'm going to put anything that has just x in it, which is just cx. And then I'm going to put anything that has no x's in it, and that's my 4a. And now all we do is match the coefficients. So we need that whatever's in front of x squared here has to match with whatever's in front of x squared here, which is 2. So a plus b has to be 2. I need the number in front of x to be, let's see, what is that? -1. So c must be -1. And then I need 4a to equal whatever's over here by itself. So I need 4a to be equal to 4. And this is my system of equations. Now for this system, I mean, I think it's kind of obvious, isn't it? Or no? Like you can figure out what a is, right? Just divide both sides by 4 on that third equation. We know a is 1. C we already have, it's -1. And to get B, all I'd have to do is go and replace that A with 1, subtract it from both sides, and I get B as 1. So that's pretty clean. There's really not a lot of work to do, but just, you know, building off what we did last class, if this were a more complicated problem, which it's not, I would have to set up my matrix, and then I would have to do RREF on the calculator, and that should give me 1, 0, 0, 1, 0, 1, 0, 1, and 0, 0, 1, -1. So that's what would happen if we needed our calculators for that. Are we good? Okay, so the original integral can now be rewritten using the expression here, right? With a replaced with 1. So 1 over x plus b replaced with 1. So x plus c replaced with -1. So x minus 1 over x squared plus 4. All right, are we good there? I didn't give this problem to you as a quiz. No? Okay. All right, now we just attack each of those individually. So I'm going to split this up. I'm going to do 2 integrals. So the first integral, you shouldn't even really have to think about too much, right? It's just natural log of the absolute value of x. Plus, now the other integral, what kind of form do we have here? Can somebody tell me like what form this is falling into? What are we seeing here?
The linear over irreducible quadratic.
Yep. A linear expression over an irreducible quadratic. And the way that I attack those, if you look back at the notes, where are my notes? Give me a moment, I'll bring my notes in here. When we were doing all this a couple of days ago, we did 8 problems when we started the section to get ready for this stuff. And number 7 and number 8 were both linears over irreducible quadratics. And so we had a procedure for this. The way that I went about it, I'm going to just do this problem over here on its own. And I'll just remember that natural log of x is going to be part of my answer. So integral x minus 1 over x squared plus 4. Does anyone remember how I went about this? If we have a linear over an irreducible quadratic.
This is where you multiplied by a 1.
Yeah, we're gonna try and make things look the way we want them to look. So we make a basic u substitution first, the denominator x squared plus 4. Okay, we're gonna make that substitution. Then we take the derivative of that. That gives us 2x dx. So we would really like this numerator to be a 2x dx, right? So I'm going to make that x a 2 first, a 2x. So I'm going to multiply the top and bottom out here by 2. I'm going to push the 2 through the top. And now the numerator is almost just 2x, right? We have this minus 1. Wait, why didn't I distribute the 2 through? No idea why I didn't do that. We have this 2x, that's great, but then we have minus 2, which is not great, right? We want it to be just 2x. So all I'm going to do then is I'm just going to split this into 2 integrals. I'm splitting it right here at the minus 2. So it's going to be plus, I need that half in front of both of them. Now this first integral should be straightforward because we know the denominator is u, the numerator is du, and so this is just the integral of 1 over u du. We know the antiderivative 1 over u du. How about this one? How are you going to deal with this one over here? Any ideas? I'm going to pull the -2 out. I'm taking a -2 out. Did someone say something? I didn't hear it.
I said trig sub.
You could do trig sub, but you would have to make that look like a square root first, right? You'd have to rewrite this as like the square root of all that square.
Mm-hmm.
You don't have, it's not, you don't have to work that hard for this one.
Would it be 1/2 tangent inverse of x squared, or x over 2 plus c?
Yep. So we've got, this is the formula 17. So going back again to the stuff that we covered, leading us into this section, what happens when we have a constant over a quadratic that's missing the x term? Remember we talked about this, is formula 17. In fact, we started this entire section out with that formula. So that's where we are right now. We have a constant over a quadratic missing the x term, got a plus in between. That's just formula 17 right there. So I think I'm ready to bring all my answer together. I have the natural log of x from earlier, plus, okay, this piece, that was the antiderivative of that. So 1/2 natural log of x squared plus 4. And then we have minus, and then now the formula for this would be 1/a is 2, arctangent of the variable here, which is x over a, plus a constant. There you go. Any questions on that? Okay. I think I want to do another one. I'll leave that there for a moment. So I thought it might be cool if we just grab a problem off my old exam. So I'm going to let you pick. There you go. So I'm gonna force you to pick between 3, 4, and 5. Which one do you want?
I say 5.
5? Okay. X cubed plus 5x over x squared plus 3. All right, let's do that one. If we have time, we'll do 2, but. All right, so we have integral. Now, there were little numbers on that integral. I'm going to ignore those for right now because we haven't talked about that. All right, so this is a test problem that I gave spring 2020, so last spring. Let's see how much work was involved here. All right, first thing is that you must recognize this is a rational function. You have a polynomial on top, polynomial on the bottom. Now, do we need long division?
No,
No, why not?
because the denominator is squared.
Yeah, so even though this is x squared, the fact that we're squaring it means that we're going to have an x to the 4th on the bottom if we expanded it out. We're not going to expand it, but we know that the degree of the denominator is 4, the degree of the numerator is 3, so no long division is necessary. Okay, so the next thing would be to factor the denominator. But you can't factor the denominator, right? Like it's already x squared plus 3, you can't do anything with. And the fact that it's squared means that it's that times itself. So it's already factored. So we have to go and do our partial fraction decomposition then. We have to do, x cubed plus 5x over x squared plus 3, that quantity squared. Now, this is a irreducible quadratic, right? But it's also repeated. It's repeated because of the 2. So that means I'm going to need to start building up pieces here. I'm actually going to have 2 pieces. The first one is going to be just the irreducible quadratic. The next one is the irreducible quadratic squared, right? And had that been a 3 here, I would have to do another one with x cubed or x squared plus 3 cubed. Luckily for us, it's just squared. Okay, what goes on the top of both of those?
AX
A and B?
plus D, then CX plus D.
So each one of those has to have a linear expression. Because they're quadratic, we have to have ax plus b And on this next one, cx plus d. So it must be linear up top. You only put a on top if it's linear on the bottom. If it's quadratic on the bottom, it has to be linear on the top. All right, and now we get to play that game. We multiply both sides by the common denominator. So all we get on the left side is the numerator. And on the right side, okay, so just remember, you're multiplying this thing by x squared plus 3 squared. It's going to go here and here. So on that first multiplication, the ax plus b stays there. One of the factors cancels, so we still have an x squared plus 3. But on the second multiplication through, you have the cx plus d and nothing else because everything cancels. The x squared plus 3 squared cancels with itself. So all you're left with is the numerator. I'm not even going to mess with the short method. I'm just going to go straight to the long method and distribute here ax cubed plus 3ax plus bx squared plus 3b plus cx plus d. Okay. I'll collect my like terms together. See, I only have ax cubed. I don't have anything else, so got that. X squared, I only have a bx squared. Okay. In terms of x's, though, I have two of them. I have a 3ax and I also have a cx. So I'm going to pull those together and then pull the x out of both of those. And then I have a plus d. Oh, I forgot the 3b. The 3b and then the plus the d. So that takes care of everything. Any questions there? Start matching up coefficients. So in front of x cubed, that a has to be a 1. So I know a is 1. Okay, in front of x squared, b has to be, what's b? Uh-oh, there's no x squared over here. What does that mean? It's a 0x squared. There is no b, that means there's a 0 in front of x squared. So that means b has to be 0. This is good. Look, we've already got a and b. This is nice. Okay, how about the next equation? We have 3a plus c, that's this piece here, it has to be the number in front of x, so that has to be 5. And then the last piece, 3b plus d, what does that have to be equal to?
0.
0, because again, there's nothing over there, that's just a constant. So 3b plus d has to be 0. Now, if I were doing a matrix, here's what the matrix would be. Do you all have any questions about the matrix? It looks like on this test, let's see, did they need to do the matrix here? We already know two things, right? We know A is 1. We know B is 0. That just comes from these two equations right there. Okay, so if you know that A is 1, then this third equation becomes 3 plus C equals 5, which means C must be what?
2.
2, right? Right, replace that A with 1, subtract 3 from both sides. Okay, if I know that B is 0, then what's D?
0.
0, okay. All right, well, this is actually looking really good. Because what this is saying is that this up here turns into this expression here with A, B, C, and D replaced with what we have there. So that just leaves me with an x over x squared plus 3 plus a 2 over x squared, 2x, sorry, 2x over x squared plus 3 squared. I'm going to go ahead and just do those as separate integrals. Any ideas on how to do those?
First one, we could do a U sub.
Okay, on the first one, we do just a basic U sub. We'd let U be what?
X squared plus 3.
Or plus 3. The derivative of that is
2x.
2x dx. I have an x dx, right? So I can just scale both sides by a half. So that whole integral becomes 1/2 can come out integral. The x dx is du, so 1 over u du. I'm showing where this is a basic u sub, right? Just a basic u substitution. Hey, you know what? Can we use the same u substitution over here? We can. If we let u be x cubed or x squared plus 3, du is 2x dx. I have it exactly up top. So that integral just turns into 1 over u squared du with the same substitution. And so the answer here is 1/2. Antiderivative of that is 1 over, I'm sorry, natural log of u, but u was x squared plus 3, plus, okay, now this one, be careful because the antiderivative 1 over u squared is not natural log, right? The antiderivative of that is negative u to the negative 1. Or if you like, you can write that as negative 1 over u. Either way. So I'm going to change this to a minus. And I'm going to put 1 over u, but u is x squared plus 3. Plus c. And we're there. I think that was a pretty fair problem. I don't think there was anything messy with that. You want to do another one? Maybe one more?
Yes, sir.
Okay. I'll just write it down. I won't bring it back over here. This one just looks nasty. I don't know. All right. So what first?
Long division.
Long division. All right, gonna move fast here, gonna move fast. 2x cubed plus x squared minus 6x plus 7. And then out here, x squared plus x minus 6. All right, in order to get x squared to turn into 2x cubed, I'm gonna have to multiply it by 2x. And that will give me 2x cubed. Then I have a 2x squared. And then I have a minus 12x. All right, so I just multiplied each one of those, right, by 2x. And now I change the signs, so it becomes minus, that becomes a minus, that becomes a plus. And I add down. So it's looking like negative x squared minus 18x, and then I bring that 7 down. I play the game again, right? What do I multiply x squared by to become negative x squared?
Wouldn't it be positive 6x? If it's plus 12x
yeah.
minus
Good
6x?
answer,
Yeah, I've been having the last 2 days just been, oh no. I made 2 mistakes yesterday. It was just like, just ridiculous things like that. Okay, there we go, right? So -1, now we multiply, we get negative x squared. Let's see if I can do basic math here. Minus x plus 6. Change the signs. Add down. So that's 7x plus 1. There we go. And that's where we have to stop, right? Because we can't turn the x squared into 7x. So this will be my remainder. So I put plus the remainder over the divisor. Yeah. Okay, so let's see where we are. Integral. This now becomes 2x minus 1. Oh, this is going to be a good, it's going to be a good little test of your knowledge right now. Okay, let's play Jeopardy. So I'm going to give you a minute here to look at this and just think about what your next steps would be. I'll give you, 1 minute. Okay. How about Nick? Nick Weens. How are you doing, Nick?
I'm doing fine.
Good. You're up on my little roster here. So how would you address this?
I honestly don't know.
Okay. All right. I appreciate honesty. That's all we can ever be, right? How about Alex Pohl?
Well, I started off by taking the derivatives of the 2x and the minus 1. So I got x squared minus x.
Okay, so you're just saying, okay, those you can do, right?
Yeah.
Those two, that's just x squared, and then minus antiderivative 1 is just x, and then plus, now you still have this, right?
Yep. And then I was trying the u sub with the bottom part.
Okay. You mean, okay, so I think you're saying you were trying to use sub, you're just going to let u be the denominator and then try and make the numerator look like that?
Yep.
Okay. So when do we do that? When we have what?
Wouldn't it be a linear over irreducible? Oh, you can reduce it.
Ah, there we go. Good. So we would do what Alex was suggesting, where we would, like the problem that we had earlier, the first problem I did today, where we let u be the denominator and we tried to make the numerator look like the derivative of it. We do that when we have a linear expression over an irreducible quadratic, but this is reducible, right? Look at this. That factors to be x plus 3 times x minus 2. So, Alex, how would you approach that?
Wouldn't it? Then it would be the partial fraction
Yeah,
decomposition.
then you just do the partial fraction. So we're just going to come over here. We're going to rewrite 7x plus 1 over the x plus 3 times x minus 2. And then each of those are linear factors. So I just do a over the first linear factor, and then b over the second linear factor. That was a plus. And then you just clear your fractions. I'm not going to show this step. I'll trust that you could all clear the fractions. And, oh, let me see here. Michael Sandoval. How's it going, Michael? How would you go about this, Michael? Would you do the short or long way?
Let's see. Should we try the long way?
You can. You want to?
Sure.
to you.
Yeah.
It's up to you. I mean, like, the short way will work. It'll be fast, but let's just do the long way. If that's the way you want to do it. I'm okay with that. So we're just distributing through, right? Clearing fractions. I'm sorry, not clearing parentheses. And then we're bringing all our x terms together. Anything that doesn't have x, just stick it off to the back. And then match your coefficients. So Michael, can you tell me what my system of equations is going to be? So can you tell me what a plus b has to be equal to?
Okay. A. Yeah, I'm not sure.
Okay, so are you okay with me? Are you okay, Michael, and everyone else? Are y'all okay with me from this step to this step? Y'all understand what I'm doing? I'm just putting the x terms together and then factoring an x out. And then anything that doesn't have an x, I'm just putting those back on the back side.
Yes, sir.
So, yeah, Alex, go ahead. What? Huh?
Oh, no, that I'm following through.
Yeah. So, Michael, once you get it here, what you're doing is you're saying, what's the number in front of x have to be? Well, look at your other side. What's the number in front of x?
Okay, 7.
7. So we know that a plus b has to be 7. And then everything that doesn't have an x in it, all of this stuff, Michael, has to be equal to what?
1.
1, right? All like that, right? So we have negative 2a plus 3b has to be equal to 1. So if you're going to use your calculator, this would be 117, negative 231. You do your RREF. Does anyone have it yet?
Yeah, A is 4 and B is 3.
Okay, so A is, whoa, what the hell? A is 4 and B is 3. Okay, so I'm not going to go through that work, but that's what you get. So that means back here when we were writing our answer down, we had x squared minus x plus this integral that we did partial fractions on. We got that A was 4, so I'm going to be using that expression right there, replacing A with 4. And then I'm replacing B with 3. And those we're real happy to see, because those are just constants over linear expressions. Anytime we have constants over linear expressions, it's just a natural log. We have to be careful. The 4 has to come out. Like that 4, you just pop it out front. Natural log of the denominator. Plus the 3 comes out. Natural log of the denominator again. Plus c. There it is.
Professor, I had a question.
Yes.
So does a reducible quadratic just mean if you can factor it or not?
Yes.
Okay, gotcha.
Reducible means factorable. Irreducible means not factorable. I'm just using the language that the book uses, and I'm using the language that you'll hear a lot when you're dealing with partial fraction decomposition.
Thank you, Professor.
Yep. Now, just as a side note, had we taken this and not realized that it was factorable, so had we done this thing where we say, okay, we're trying to do the integral of 7x plus 1 over x squared plus x minus 6, and we made the substitution of the denominator, the derivative of that would have been 2x plus 1 dx. We would have had to have tried to turn this up here into 2x plus 1. So I would have factored a 7 out first of the top. I would have forced a 2 over 2 in here, pop the 2 back in. So now I have 7/2 integral 2x. I know I'm working fast, but I'm just trying to get you to see that this way would be doable, but long, okay? So I'd be there now. Now I need that to be a plus 1, so I would do a hidden 0 in here. I would do a plus 1 minus 1 right there. So that would turn into 7/2 integral 2x plus 1 minus 1 plus 2/7 over this. Then I would split this down the middle. So my first integral would be 7/2 2x plus 1 over x squared plus x minus 6 dx. Okay, so that would be these two over this, which is doable now because now the top looks exactly like the derivative of the bottom. But what you'd still have over here is plus 7/2 integral. You'd have to put these two together. What is that? Negative 5/7 over x squared plus x minus 6 dx. And the question would be, how do you deal with this? Well, you have two choices. You could complete the square on the bottom, or you could factor the bottom and then use partial fractions, right? Those are your two choices. But if we do partial fractions here, then shoot, you know, like we should have done it earlier because it worked out earlier. You know what I'm saying? Like, so if you go down this road, you're going to wind up doing a lot more work. You'll get an answer, but you're going to do a lot more work. So always be looking when you've got a linear over a quadratic. Make sure that that thing doesn't factor. If it factors, go to partial fractions. If it doesn't factor, you got to do this. So like if that didn't factor, we would complete the square here. All right. So I think, you know, I don't know, would you agree that those questions on the test were within reason? I mean, there was nothing too crazy there. This one was okay. This one's okay. This first one, or not the first one, it's the second one, obviously. This one right here, that one is a linear over an irreducible quadratic. So I'm forcing you in that problem to do the u and make it, bring in the 1 and make the derivative of the top look like the bottom, you know, I'm sorry, make the top look like the derivative of the bottom. Like I'm actually forcing that to happen in this test. So you have to demonstrate to me that you know that technique. And I can assure you that on your test, you're gonna have that too. Somewhere in there, you're gonna have to show that. I'm not sure how the third one works out. I can see the denominator though. Like this denominator factors to be, pull an x out, get x squared minus x minus 2, and then that factors more, x minus 2, x plus 1. So it looks like that one you're just going to do with partial fractions. You're going to have 3 distinct linear factors. So you're going to do like a over x, b over this, c over that, go find a, b, c, you're in business. So in terms of difficulty level in these problems, it's, if you've done the homework, I think that these problems are on the lighter side of some of the homework problems. And that's because this test is an hour and 40 minutes, right? So you only have a certain amount of time to do it. So I just want to make sure you know how to use, know how to do the basic ideas. Okay, anything else with this section you want to talk about?
On the exam next week, are there going to be definite integrals?
Yes, that's what we're going to talk about today. So our exam, I don't recall. It's not on Monday, is it?
It's next
It's on
Wednesday.
Wednesday.
Wednesday. Okay, so we still have another class period before this. But I would spend all of your weekend reviewing trig sub, partial fractions, trig integrals, trig sub, all that, like 6-2. On the test that I gave here, I didn't do a lot of trig sub, okay? But I think we're gonna have maybe like 2 trig sub problems on this test. Here there's 1, but on your test, I think I'm gonna do 2 trig subs, maybe 2 partial fraction problems, right? Maybe 3. So, you know, you're looking at like 5 problems there, and then maybe an additional problem with the definite integral stuff. So I still think you'll be in the neighborhood of like 5 to 6 problems, but when you're reviewing this weekend, take a lot of time to go back and look at 6.2 and 6.3. Yeah. 6-4, there's nothing from 6-4, okay? And I'm not going to even talk about 6-4 other than, I think I told you this before, 6-4 has to do with using computers to solve integrals. And so when this book was published, there wasn't even like Wolfram Alpha when this book was made, or maybe Wolfram Alpha was just in its infancy. So nowadays we know that we can go to multiple websites, type in something and integrate it, and the computer will do it for us. So all that book was just saying is, hey, we've got technology out there that does this. Now we have it very, very readily available to us. All right, we good? Gonna move on. So 5.2, 5.3, 5.4, there's no homework assigned from this yet because I want to talk about it first. What I'm about to do is I'm taking these 3 sections and I'm combining them into like one lecture and picking the most important parts of each lecture. So you'll see, just wait till we get to the end. When I talk about what's going to be for homework, I think you'll understand that it's not a huge, we're not taking a huge leap here. In fact, we can kind of take an exhale here and be like, okay, we're done with the techniques of integration, all right? Now we can move on. So here we go. So you want to almost kind of clear your mind a little bit here. And just, I mean, we still need to know that, we still need to know how to integrate, but I want us to kind of start with like a fresh kind of look at things. So what we're going to be talking about now comes from this problem, the area problem that was a problem for humans for a long time. So we all know what the formula for the area of a circle is, right? If you were asked to calculate the area of a circle, we all know that the area would be pi r squared. And we all know that pi is approximately 3.1415. But that number keeps on going forever, it never repeats itself. It's an irrational number. So the question is, where did this formula come from? Right? So where did it come from, right? How did we come up with that formula? I say we as in humans, right? Because we didn't just like stumble upon it, didn't fall out of the sky, right? We had to actually generate this formula. So for a long time, historically, humans were trying to measure the area of things that were not nice, straight, shapes. We could always measure the length of a straight line easily, but when it came to a complicated shape, something with curves on it, we had trouble. And the circle is the most natural one to look at as like the first issue we had, all right? So one way we could do it, all right, one way we could estimate the area. Well, does anyone have an idea of how we might be able to estimate the area? Just imagine you're sitting, you got a piece of paper, you can draw a nice perfect circle. You get like a little needle with a straight, maybe a string, and then you put your pencil and you go around, you draw a nice circle. You've got a nice ruler next to you. How could you estimate the area of that if you didn't know pi r squared? Any ideas?
Would you draw like squares or rectangles?
Okay. Inside the circle?
Yeah.
Okay, so yeah, you could do this. You could say, let me draw like a square or rectangle in here. If you take your time and you draw that very carefully, you could calculate the area of that, right? And we'll just call that rectangle 1. And then right now, obviously, rectangle 1, that area is less than the true area. I'm just going to put area with true subscript. Does everyone agree that that rectangle is smaller than the true area of the circle? Okay, but you could get better. You could maybe throw another rectangle in here. Call that rectangle 2. Maybe another one on this side. Call that rectangle 3. Maybe try and squeeze another one in this corner. Maybe a small one up in here. And you start to get all these rectangles in here, right? So maybe you squeeze like 30 rectangles in there. but you still know that rectangle 1 plus rectangle 2 plus rectangle 3, all of those together, however many you have, let's say you have 30 of them, you still know that all those added together is smaller than the true area. Do you all agree? Because we still have these little gaps that we're not accounting for, these little spaces that we can't quite get our rectangles in. But the more you do, the better your approximation is going to be, right? The more rectangles you can squeeze in there, the smaller your error is going to be. Okay, I like that idea. All right, so let's stick with that idea. But now I'd like for us to do it a slightly different way. I'd like for us to draw a rectangle that's on the outside of the circle like this. Well, that's a square, but we'll just call it a rectangle. Okay? And let's call that, now we've kind of started over. In fact, I'll go with a different color since I've started over. So we'll call that rectangle 1. Would you all agree that rectangle 1 is bigger than the true area now? Yeah, the area of rectangle 1. So I have some error, right? I have these spaces right here where that's too much area. So what I could do is I could fill that with a rectangle. I'll call that like rectangle 2 and 3 and 4 and 5 and 6. And I can start subtracting those from rectangle 1. So in other words, I could do rectangle 1 we know is too big, but if I take away rectangle 2, take away rectangle 3, take away rectangle 4, and I keep doing that for all, I don't know, let's say I do another 30 of these things. Do you all agree that that's still too big? It's still bigger than the true area? Because we still have these little tiny spaces that we can't get our rectangles in. So here's where we are. We have a way of coming up with a number that's smaller than the true area, and we have a way of coming up with a number that's bigger than the true area, right? Like we actually calculated what that number was and what this number was. They're different numbers, but we can compute those. So what we have is the true area squeezed between two numbers that we can calculate. So maybe we've got it squeezed down where these two numbers on the outside are only off by maybe 1/10. Well, the more squares, more rectangles we can draw, the better and better our approximation comes, and the smaller that little window becomes, and we start to squeeze the true area between two numbers. Does that make sense? But we have to be able to draw a lot of rectangles. It's going to take us a lot of time, and it's going to be somewhat exhausting to do this, right? I mean, can you just imagine someone back before computers, like before we had a formula for area of a circle, trying to figure this out? Well, the Chinese were the first to really do a good job of this. And what they came up with is the Chinese were able to determine that the area of a circle was pretty darn close to 22/7 times the radius squared. That's what they were able to determine. 22/7 was their approximation of pi. It's not the same number, but if you get on your calculator and you do 22/7, you'll see it's 3.1428. And it keeps, you know, there's more decimals, but that's approximately 3.1428. It's not pi, but it's correct. It matches with pi out to the nearest hundredth, which for like ancient calculations is pretty damn good. But they did it using this method of these squares. Now, that method has a real name, all right? That method actually has a real name. It is called the method of exhaustion. And that's a good name, right? The method of exhaustion, because anyone who is actually going to sit there and calculate the area of like 1,000 rectangles within a circle is going to be there for, you know, weeks probably getting it to be precise, and that's exhausting. So, but it, you know, it's a way, right? It's a way. It's not very efficient, but it's a way we can do it. Another way we could do it is to, and this one is perhaps more efficient, is to imagine that we take a circle and instead of doing rectangles inside of it, do triangles. Because if I do triangles, I know that the area of a triangle is 1/2 base times height. And I also have other formulas for areas that make it easy to calculate, or for triangles that make it easy to calculate areas. But I could do maybe like one triangle there, maybe another one, another one, another one. That would be an approximation, right? Everything in yellow is error, but that's one approximation. I could do something like this where I change the size of the triangle. So I do a triangle like that, and then I start putting those in the circle like this. And now I've got all these triangles I can calculate the area of, and my error here in yellow is getting smaller, right? And what would be better is if I could make my triangles, really small, like really, really small, like that. And then start putting those triangles around the circle. Now, I've got a really good approximation, right? What would be the ideal situation then? How many triangles would I need in order to get the true area?
An infinite amount.
An infinite number of them, right? But there's something wrong with that idea. Think about what you're saying. If you're saying that you want to have an infinite number of triangles, right? An infinite number of these, what would happen to the area of each triangle individually? So think about what's happening. The more triangles you have, they become more narrow, right? That angle starts to close. And so if you had an infinite number of triangles, wouldn't that angle close down to nothing? If it closes down to nothing, now instead of being a triangle like this, it's now a line segment. And what's the area of a line segment? Well, you have no area. Line segments only have lengths. They don't have area. You need a second dimension in order to get area. So do you see that even though like in our minds, we may be like, look, if we could somehow get an infinite number of triangles in there, we could find the area. We instantly create a new problem that an infinite number of triangles means that the area of each one's going to 0. Right? Okay, so think again, historically, you've got this idea that's very clear. If we can just get more of these in here, create an infinite number of triangles, then we could find the area, but the area is going to 0 because they're getting smaller. What subject was created down the road? Because we're talking ancient times, they could think this through, but what subject came along? What topic, what came in to the math realm that allowed them to deal with this idea of, oh, it's going to infinity, oh, it's going to 0. Where do we see that? Where's the first time you saw that?
Calculus.
Calculus, right? The limit, right? The limit. The limit was developed by Isaac Newton and Leibniz, the two fathers of calculus, as a way to get around, as a way to attack any problem that had infinite things going on in it, or things that were going to 0 or something like that. The limit allowed us to still get a numerical answer for an expression that perhaps doesn't make a lot of sense, right? Like back in Cal 1, when you first are being taught the limit, you could have something like this. What's the limit as x goes to 2 of x squared minus 4 over x minus 2? Well, if we let x go to 2 here, we wind up getting 0 on top and 0 on the bottom. So we get 0 over 0. But we find out later that, you know what? We can still get an answer from this. We can factor the numerator out, x plus 2, x minus 2. We can cancel these factors. And so this limit is actually equal to 4. So even though you cannot actually plug 2 in, right? We're not allowed to ever plug 2 in, because if we plug 2 in, we get 0 to 0. But if you get closer and closer and closer to 2, you get an answer that's closer and closer and closer to 4. That's exactly what we want to say here. I want an infinite number of triangles. Now, I can't actually put an infinite number in, because if I put an infinite number in, the area goes to nothing. But in the limit, as I let the number of triangles go to infinity, the area must go to a number. It's a limit. Does everyone see that? That is why when calculus came along, we were able to attack the area problem precisely and be able to get the pi. Now, we will actually show it. I'll prove it to you. Maybe today, I doubt it. But I'll show you where the area formula for a circle comes from, all right? We're going to generate it ourselves, and we're going to use antiderivatives, and we're going to use, we're going to do it, all right? So that's the idea. Now, let's now imagine that we are going to start from scratch, all right? We are going to imagine again that now we have calculus, right? Like now we're armed with calculus, and we want to go attack the area problem for a circle. Here's the way we're going to do it. We're going to not attack a circle. We're going to attack just an arbitrary function. So we're just going to take some function, y equals f of x, and we're going to ask ourselves, is it possible for us to, let's say, start at some point A, end at some point B, is it possible for us to calculate the area below this curve? Is that possible, right? So that's the question that we're going to ask. Now, why is this better than going after a circle? Let me just show you real quick why this is even better than going after a circle. Because if I then wanted to go attack a circle, then what I could do is just look at the curve that gives me the first quadrant of a circle. This curve right here, like the first quarter of a circle, right? That right there is, there's definitely a function. There is definitely a function. Now, you may not know what it is, but it is there, okay? I'm gonna put a question mark. There is some curve that draws that circle, that part of the circle. So do you agree that if we could find an efficient way to find the area of just that, find an answer, then just we multiply it by 4 and we'd have the area of the whole thing, right? So by doing this, looking at it generally for any function, then we can apply it to a specific function to get the circle. But we can do it for everything though, right? As long as we have a curve, we can get this area. So the extension of this idea to different things is kind of like boundless if we can figure out a formula for the area, right? Would you agree with that? All right, so how do we attack this? Well, one thing we could do, let me get rid of this. One thing we could do is this. We could say, all right, and I want you to be very clear on something here. Everything I'm highlighting green right now, we are given, okay? We know this. So somebody must hand us a function, whether it be x squared or some square root function, whatever it is, somebody has provided it to us. So maybe it's the function f of x equals x squared, okay? But that's given to us. And then they also give us these 2 endpoints. Maybe that a is 1 and maybe this is 4, right? But that's all information we have. We know the function itself and we know these 2 endpoints of where we're looking. So if we're given that, one way I could approximate this, is to draw a rectangle that has as its base that distance from here to here, as its height the distance from there to there, and I just draw a rectangle over and down, that rectangle would have a certain area, right? That would be an approximation, but that approximation would suck, right? Because we're missing a bunch of stuff, aren't we? Yes? But let's still try and figure out if we could figure out a formula for just that rectangle, just that one. So I'm going to call that rectangle 1. Okay, can somebody tell me what the area of that is? Area of any rectangle is length times width, or however you want to say it, base times height. Just the two sides multiplied, right? So can someone tell me how wide that is? We're not using 1 and 4.
Okay. So I guess A plus B.
Close.
Is
A
it B
times
minus A?
Isn't it? Okay, so if we were using 1 and 4, wouldn't this be 3?
Right.
And so you're just doing 4 take away 1, right? 4 take away 1. So do y'all understand that the width of that rectangle, actually, yeah, I'm going to put it here. That's the width of the rectangle. The width would be B minus A? Yes? Now, how tall is this rectangle? Well, where is the corner of the rectangle? It's right here, right? And that's on the curve. And that point came from plugging this point into the function, and it spit that number out, right? So can someone tell me in terms of the function what that is? Not x squared, just generally in terms of the function, what point is that? If I asked you for the coordinates of that point, can you tell me the coordinates of that point?
It'll be B,
B got plugged in, and what got spit out?
Y.
Y, which is the function's value at B, right?
Okay.
It's whatever the function is at B. We don't know the function, but that's what it is, right? So I'm going to put here times f of B. All right, do we have a formula? Remember, you have the function, someone gave it to you, and you know what A and B are. Do you think you could calculate that if you knew what the function was and you knew what A and B were? Could you get a number from this?
Yeah, I believe so, yeah.
Yeah. Now, it would suck, again, it would suck because you got all this part in here that you basically added, but it's not there. All right, we did one rectangle and that's what happened. How would we get a better approximation?
Add more rectangles.
All right, add more rectangles. So now let's take that same picture. Instead of using one rectangle, this time I'm going to use 2. So what I'm going to do is I'm going to cut this interval in half. From this point, whatever it is, I'm going to plug it in. Wherever I hit the function, I'm going to draw my first rectangle. Oops. Try that again. Go straight across and down. That's rectangle 1. And then my second rectangle hits here, goes across. Notice it's not the same height as the second rectangle. Yes? All right, now I want us to come up with formulas for the areas of these. All right, I want us to look at these, but we're gonna do this a little bit different. This is gonna seem weird, but trust me, there's a reason why I'm doing this. Let's talk about the width of the rectangles, the width, how wide they are. So this rectangle has a certain width, this rectangle has a certain width, right?
Would it be 1/2 A minus or B minus A
1/2 of what?
of B minus A?
Okay, yeah, so look, remember up here, this width up here was B minus A? It was just B minus A. It was whatever one endpoint was minus the other one. Here, isn't it that same distance, B minus A, but we've cut it into 2 pieces? So isn't it half of that? Each one of those is half. So this is B minus A, half of it. This is b minus a, half of it. What if I had done 3 rectangles? How wide would each one be? B minus a over 3, right? If I did 10 rectangles, b minus a over 10. Yes? Okay, so I'm going to start writing the formula here. The rectangle 1, I'm going to put the width in the back. That's how wide it is. I forgot to put over here, sorry, over here when I put width, put over here height. That's how tall the function or the rectangle was. The width of it and then the height of it. Right? The width and then the height. Here with rectangle 1, the width is this. What about rectangle 2? What's its width? Same exact thing, right? The heights are different though. The heights are different. So I want to highlight for this first rectangle, I'm going to highlight the point that we plugged in. It's that one, right? We go up, we plug that into the function, and what that does, that gives us like an ordered pair there. It has an x and a y coordinate. Let's talk about the x coordinate. This is a part that's going to be a little tricky when I do this, because you're like, why are you doing it that way? So let's see if this makes sense to you. Do you agree that to get to this point, what I could do is start here at A, and then add to A whatever this jump is, whatever that distance is. Do y'all agree? So I could say add b minus a over 2. That's the x coordinate there. Do y'all agree? Start at A and then jump over one width. Using that same logic, look at this point here. Couldn't I say that that point is start at A, but add to it how many jumps? 2 jumps, right? 2 jumps. So I would add to that 2 of the jumps of b minus a over 2. Now, I know you're going to look at both of those and be like, what? Why are you making that so ugly looking? But trust me, this is going to be a good thing, all right? So agree with me or not. The height of the function, the height of the first rectangle is whatever I get when I plug into the original function, this point right here, which is a plus b minus a over 2. And then the height of the second rectangle is what I get when I plug this one in, which is a plus 2 times b minus a over 2. Yay or nay? This is a good time for you to ask a question. No? All right. We need more rectangles. 2's not enough. What we're trying to do is get something like this going. We're trying to have a function where what we do is we start breaking it up into 2 pieces, 3, 4, 5, 6, 7, 8, 9, 10, right? And we start to try and put in hundreds, thousands, millions, an infinite number of rectangles. We're trying to get those areas, right? Does that make sense? So we start off with 1, then we go to 2. Oh, 2, and then 3 and 4, right? So I'm going to give you a minute now. I want you to think about this. If I take this same problem and I want you to cut this into 5 rectangles. I want to see if you can figure out what the formulas are for the areas of all 5 rectangles. Okay, so I want you to put in here 1, 2, 3, 4, 5. Sorry, those are all the same width. It doesn't look like it, but there's 5 of them in here. Now, my hint to you, because I'm going to give you a few minutes to think about this, my hint to you is just to follow this pattern right here. There is a pattern developing in this formula. There's something happening here, okay? So let's see if you can. I'm going to give you a few minutes, then we'll ask for volunteers to help. I'm going to ask for anyone to tell me all of these have the same width. Do you all agree? The width of each of these rectangles is the same. Can somebody tell me what the width of each rectangle is?
B minus A over 5.
B minus A over 5, right? Okay, so each of these has B minus A over 5, B minus A over 5, B minus A over 5, right? So that piece right there, the width, is just the width of each of the rectangles, and they're all the same, okay? Now, does someone want to share with me what the height of the first rectangle would be? So what would be the height of the first rectangle?
A plus B minus A over 5.
So the function, right, evaluated at, what did you say?
At A plus B minus A over 5.
Okay, so does everyone see that what that is saying is for rectangle 1, we are going to go to this point right here and go up and plug it in. So that point right there is starting at A and adding to it one jump, one width of one rectangle. Right? Alex Pohl, you okay with that?
Yeah.
Got this look. Okay, all right, right? So I'm going to throw a number in here that is there, but you don't really see it, you don't need it. I'm going to put a 1 right there. Y'all see where I put that 1 there? Because I want you to understand that's A plus 1 jump. Okay, what would the next one be? Anyone?
Same thing, but you put a 2 in place of that 1 that you put.
Yeah, so this one, we're going to do A, and then we do 2 jumps. Plus 2 of those jumps. Whatever that is, you plug it in the function, it'll throw out the height. And we keep doing this, right? Every one of these expressions is going to be exactly the same. This one will be a 3, a 4, and a 5. Make sense? Okay, we're getting somewhere now. What if we had this, and now in here, I want you to do n rectangles. N of them. See if we can, again, find the pattern. What would the area of the first rectangle be? All right, well, let's start with the width. How wide is it?
B minus A over N.
B minus A over N this time, right? Not 5, N, because we're cutting it into N rectangles. All right, and then we're going to have the function evaluated at A plus one of those jumps. One of the jumps. How big is the jump? B minus A over N. Make sense? And then the second rectangle would be the function evaluated at A plus now my second jump, 2 jumps I should say, whatever that number is, and then times the width of the rectangle. And I do this all the way down until I get to my last rectangle, which should have an area of the function evaluated at A plus n jumps, right? We're taking n jumps of B minus A over N times B minus A over N. So if you look at this, the formula for each of these rectangles, there's only one thing that changes. Every formula is exactly the same except for the number 1, 2, 3, 4, right? That changes, which of course changes what comes out because we still have to plug it. We still have to plug these numbers into the function. We don't even know what the function is. I mean, someone's given it to us, but we'd have to calculate those. But there's only one little thing that's changing, right? So would you agree that we've come up with kind of a nice little compact way of representing the area of each of these rectangles? So at this point, we're going to take a short detour and we're going to just talk about what's called sigma notation. This is something you may have seen, hopefully you have, in college algebra. So if we ever have a bunch of things being added together that all have something in common, we have a nice condensed way of writing it. In other words, if we have something, I'll call it a sub 1 plus some other thing, a sub 2. We don't know what these are. There's just a list of things we're adding together. And let's say we have n of them. So we want to add n things together. We have a very compacted way of writing this. We write the Greek capital letter S, that's sigma. We put on the bottom what's called the starting index, which is k equals 1. And up here is what we call the stopping point, or the ending index. And then here is almost like the argument of the function. We put a sub k. So the way this notation works is as follows. The sigma says, hey, we're about to add a bunch of shit together. K equals 1 says we're going to start with 1, replacing k with 1. And we'll keep doing that. We'll put in 1, then we'll put in 2, then we'll put in 3, and we'll stop when we get to n. Now, what are we plugging k into? This expression. So let's start. Let k be 1, replace k with 1 here, we get a subscript 1, right? That's this. Then we say plus. Now we let k go up to 2 and plug 2 in here. That gives us this one. Then we do plus, and we plug in 3, and that'll give us this one. And we keep doing this until we get to n and we stop. Make sense? Okay, so let me see if you understand this or not. If I write this, what would this be? So you start with k being 1, you plug it in here, you get what? 1 squared, which would give you 1. Plus, now let k be 2. What would you get if you plug in 2?
4.
4. Okay, now let k be 3. Plug it in, you get
9.
9. Now let k be 4. Plug it in, you get
16.
16. And that's when you stop, right? That's when you stop. And so if you add those up, I don't know, 5, I can't add 20, 30? Is that 30? All right. So this is just notation, okay? It's just something you should be familiar with. So let's go back up here, because if I'm going to do the area of this, right? If I want to do the area, if I want to estimate the area of this, then what I need to do is take all these and add them up, right? I need to add those. So that means I need to do rectangle 1 plus rectangle 2 plus rectangle 3 all the way out to my nth rectangle, right? What's sigma notation for that? Sum k equals 1 to n of r sub k. Do y'all agree with that? If I let k be 1, I have r sub 1. There. Let k be 2, I've got r sub 2. K be 3, let r get r sub 3. And I stop when I get to r sub n. Yes? However, this is the same as the sum k equals 1 to n. Now look at each of these. Remember what we said, this was the vital part. The only difference in these formulas is that that number right there, 1, 2, 3, 4, 5, 6, n, that's the only thing that's different in all the formulas, right? And aren't those numbers matched up with the subscripts? So I could rewrite this as f of a plus k times b minus a over n times b minus a over n. And so the only thing changing is the k. So if I plug 1 in, I get, if I replace that with the 1, I get the first rectangle's formula. If I replace that with 2, I get the second rectangle's formula. And then the third, fourth, that's all the way down. Does that make sense? All right, we're almost there. We're almost there. So I'm going to write this down. the area is approximately the sum k equals 1 to n f of a plus k times b minus a over n times b minus a over n. Remember, this was the height of each rectangle, and this was the width of each rectangle. Height times width gives you area. So this is a nice compact formula that allows us to add up the area of n separate rectangles. Now, do you all agree that this still sucks? Like if we had 100 rectangles, we'd still have to calculate the area of each one. If we had 1,000, we'd still have to calculate the area. All I've done is I've put this in a very nice condensed compact notation for us. Yeah? But theoretically, going back to the very beginning of this whole topic, what would the true area be then? Not approximately equal. What would the true area be? And I think, was it Christian that said this when we were talking about circles or whatever? I don't remember who said this. If we were to try and get the true area, how many rectangles would we need?
Yeah, it was infinity.
Yeah, you need an infinite number of rectangles, don't you? But we already know that that won't necessarily work, because if you go back to this picture, or better yet, go back to this picture, the more rectangles I get, what can you tell me about the width of the rectangles? The more I have, the width is starting to go like this, right? And so if you go to infinity, you're eventually going to smash that width down to 0. And if you have a 0 width, you have no area, right? This is exactly like what we had with the circle. But what saves us? What saves us from actually having to be at infinity?
A limit of x approaching to infinity.
Yeah, we take a limit here, right? So if we take the limit as n goes to infinity of this sum, then that should be the true area. That is the definition of the area underneath the curve between the points A and B. So if someone gives you a curve and they want you to find the area beneath that curve from A to B, you want that area. That area will be the limit as n goes to infinity of that sum. Now, I am going to agree that that's still like an impossible thing to do by hand, because that's a lot of calculations to do, right? And then go to infinity. This could be very, very bad. All right. So even though it's a nice notation, and even though we've got everything looking pretty and stuff here, this is still unworkable. All right. It's not something we want to do. So why am I showing this to you then, if we're not even going to use it? You'll see. Then came, after this development, these are called Riemann sums. After this was developed, this idea, came what is known as the fundamental theorem of calculus. Fundamental theorem of calculus. Most mathematical subjects, major subjects, have what they call a fundamental theorem, which is a theorem that is just the foundation of that course. You could argue that limits are the foundation of calculus, but this right here is the fundamental theorem, which what it does is it's going to create the link, the bridge between a derivative and antiderivative. It's going to connect the two together. And here's what this theorem says, and it's got different versions. The version I'm going to show you is the one that's going to be most useful to us. It's called the evaluation version. Here's what the theorem says. Now, keep in mind, a theorem is a mathematical statement that is true, and it's been proven to be true we are in no way going to go through the proof of this. I can remember the first time I proved the fundamental theorem of calculus. I was, I think, a junior or senior in my math program, and I was taking a course called Real Analysis, and we had to do, that's where you actually do real theorem proving. And I can remember still the day I proved this, I was having a lot of trouble with it. I was working on it for a long time, several days, if not weeks. And I fell asleep, and in my sleep, I actually like dreamt the way through the proof. I know that sounds ridiculous, but that happened to me a lot. I mean, it probably happened to you, whatever field you're in. Sometimes when you're asleep is when your mind works most efficiently. So I woke up and I wrote it down on a whiteboard. I had the proof, and I was so proud of myself. I put it in the back of my car, and then I went over to my parents, and I was over at my parents, and I told my dad, I said, hey, you know, I have this proof I did. I got it, like in my sleep, I figured it out. And I went to go show them, and I opened up the back of the car, and they had this real big fluffy dog, okay, this white dog, and his name was Nanook. Nanook came running around, jumped in the back of the car to go for a walk or a ride or something. He was all excited, and he sat on my proof and just like basically erased my proof with his fluffy fur. And the good thing was I already knew the proof, like I understood it now, so I could reproduce it. But I'll never forget that, being like, oh, well, there it was, it's gone now. But okay. Fundamental theorem, I have 6 minutes. Here's what the fundamental theorem allows us to do. All right, this is what it gives us. This is super powerful. It says this. It says if you have a function and you're going to look at it between A and B, and you'd like to know what that area is, here's what it is. The area is the antiderivative. Well, let me write it this way. Let me write it. The area of that is just the antiderivative of the function at B minus the antiderivative of the function at A. So you have to understand that this function right here is y equals little f of x. The antiderivative of little f is capital F. So this is it. This is the theorem. It's so simple. It's mind-boggling how simple it is, but the power is, you can't even begin to understand how powerful this is. But let's look at just how simple what this is saying, it, you know, what this theorem is telling us. I'm going to do it with a specific example. So let's say we had the function y equals x, let's just go with x squared, okay? And let's say we wanted to go and look between 1 and 4, and I wanted to know that area. According to this fundamental theorem, all I need to do is figure out what the antiderivative is first. Okay, so can someone tell me what the antiderivative of this is? I'll write it down over here. What's the antiderivative of x squared?
X cubed over 3.
X cubed over 3, or 1/3 x cubed, right? That's capital F. Now what I do is I just take that capital F. First thing I do is I plug in B. B is this number, 4. And then what I do is I subtract from that antiderivative at 1, which is the other endpoint. Whatever this number is the area. So I'd have to go 1/3 times 4 cubed minus 1/3 times 1 cubed. And this gives me 4/16 minus 1/3, which is 15 over 3, it's 5. Am I doing my math right? No, shit, I totally jacked that up. Why did I
Yeah,
jack
I
that
think
up?
4 cubed is 64.
Yeah, this is, hold on, this is 64/3. I don't know, I canceled something, I was just being dumb. Okay, so this is 64/3. So this is 63/3. Is that right? My math still seems off. 21? Four times 4, 16 times 4, 64 over 3. Okay, there it is, 21. That's the area under there, exactly 21. Now, the fact that it's a nice number is just, it just happens to be 21. Your answers aren't always going to be nice numbers. That's it. That's what the fundamental theorem is telling us. That's all you have to do. But the key to it is you have to be able to find the antiderivative, right? If you can't find the antiderivative, you can't use the formula. So that's why we spent all this time being able to figure out antiderivatives, because now we can actually use it for something. So now I'm going to write the fundamental theorem of calculus in the version that you are going to use. So if y is some function of x, then the on some interval AB, so you're given some interval AB, then the area is equal to, we're going to use this notation. Now you've seen that notation before, right? Doesn't that mean go find the antiderivative of this function? Right? But we're going to add something to it. We're going to add a number down here and a number up here. Those are called our limits of integration. I'll talk about that later. I'll label this, and we're down to 2 minutes. But these are called our limits of integration. And that's it. That's the new notation that we're going to use. This is telling you to go find the antiderivative of this function and then plug in these 2 points, right? That's what it's saying. So the way we write it is this. We write capital F of x, and then we put a bar and we put A and B. So what this first little statement does is it allows us, if we're working through a problem, I'll do a problem right above this. Let's do the problem we were just doing. Okay, so that's the problem I just drew here. We have the function x squared. We're looking between 1 and 4. That's asking you the same to find the area. First thing here, this allows you an opportunity with your paper and pencil to actually write down what the antiderivative is first. Like you write it down first. Then you have the 1 and the 4. At this point, you can just do the formula, f of b minus f of a. So we would do here equals, now we plug the 4 in, 1/3 times 4 cubed minus 1/3 times 1 cubed. So there's some new notation here. We've got the a and the b are now part of our notation. This part right here is like an intermediate step that we're going to want to write down, and then we have to do the actual calculation. All right, I have 1 minute, so I'm gonna wrap this all up. Why did I go through all of this? Why did I do this? Here's why. You see this? This is not just a summation, right? It's a special summation. It's a sum that we're taking a limit of, right? It's a sum that we're taking a limit of. This right here is just the height of the function, right? That's just the height of the function. And this right here is the width. So maybe we can have a special notation for this, a limit of a sum. Okay, yeah, let's use this notation. It's an S that's stretched out. That's the integral sign, right? The integral sign is saying we're going to take the limit of a sum. Now, what are we taking the limit of? What are we going to take the limit of the sum of? This right here. Isn't that just the function evaluated at different points? Okay, so it's just the function evaluated at some x values. What about this piece right here? The width. Isn't that how much we're changing by each time? Like the x, the little change in x? Those are really tiny little changes in x. Let's call those dx. Little dx's. This is your height. This is your width. And you're adding them all up. Integral says you're going to add a bunch of shit up forever. What are you adding up? The height times the width. I'm just trying to get you to see that the notation makes sense now because it corresponds to geometrically width times height. Okay? All right, we're out of time. So there's not really anything new. These are called definite integrals. I still need to talk about this, and I'll do that next class. All you would have to do now, if you wanted to do your homework from I think I'm going to give you some problems out of 5.3. I appreciate y'all hanging out for an extra second here, an extra few minutes. From 5.3, yeah. From 5.3, I would look at like the first 10 problems. This is page 289. First 10. So they give you problems like this. I'm just going to make it up. So they want that. So they want you basically to find the area under that curve between -2 and 2. There's only one new thing from this. You still have to find the antiderivative. right? You still have to do that, but now you have to remember you're gonna have to plug in these two numbers into that answer. So you always start off by plugging in the 2 first, and then subtract from that what you get when you plug in -2. Get that number, that numerical answer represents the area. So do you see, as far as calculus is concerned, there's nothing new, still antiderivatives, but it's just a final step of plugging a number in, plugging 2 numbers in. All right, that's all we have. Make sure you complete all your homework from partial fractions. Try and do those problems if you can. We'll come back on Monday and we will do more of this, okay, fundamental theorem, and we'll talk about the test, and then you'll have your test on Wednesday.
All right. Thank you. Have a good day.
Yep. Okay, sorry this seems so rushed. I knew I was not gonna have enough time. I was trying to get through as fast as I could, but anyway, y'all take care. Have a good one.
You too. Thank you.
Hey, sir.
Yes.
Those